15. Let me share my screen. Can you guys see my screen?
Yeah.
Okay, great. So, hi everyone. My name is Sarah, and so yesterday we had a lecture about to understand how R works, and today we'll be having like a demonstration to actually like try everything that we learned yesterday and see how it works in R. And so to begin, let's begin by learning how R works. So as a reminder, R has different compartments, like it has this text editor. So this is where you're gonna run all your codes. It has the R console. So this is where we're gonna use this a lot to test a lot of our codes. We have the environments, the history tab. We have all of these tabs right here, and we'll be learning about them today. Okay, so let's try to start by a simple example. So let's do like 4 plus 6. And then to run a command, you need to hit command plus enter. Otherwise, so when you do this and you hit just enter, it's just gonna take you on the next line. So in order for you to run, oh, I'm sorry. Like, let me do an example here. So if you do 4 plus 6, is just gonna take you on the next line. So in order to run your commands, make sure that you hit command plus enter or command plus or Windows plus R if you use Windows. And the command plus enter is just for Mac users. Okay. So you'll realize that if you run this code right here, nothing is going to be saved here. Like you're not going to see any results saved. And in order to save your results, you need to use some assignment operators. And we either use an equal sign or we use this sign right here, which is what I like to use. And you basically have to name it. Like, what do you want to call it? How do you want to save it? So in my case, I named it X. So you can name it however you want. So you can do X, and then you do this assignment operator, and then you type in what you want to make, what you want to do. In this case, 4 plus 6, you hit command enter, and then you're gonna see that this is saved right here. So you're saving X as a variable and has a value of 10, okay? And if you wanna see like, okay, what does X equal to? You can just type X and then do command enter, and you can see that X is equal to 10. Okay, so remember yesterday we saw how R is case sensitive, meaning that lowercase are gonna be treated differently from capital cases, okay? So in this case, we named it X. So if we decide to name it capital X like this, so we're assigning the variable to be named X, and then we do the same example, 4 plus 6, you hit command enter, you're gonna see that these are saved in 2 different ways. So there is X here and there is another bigger X here. So they're gonna be treated differently. So those are the things that you need to pay attention to because R is case sensitive. Okay, so now let's talk about how to view and delete objects. So to view and delete objects, you first have to assign, like I said, so you just name it. I named it A, and I want my A to be equal to 3. You hit command enter to save your results. I named it B, and I want my B to be equal to 10. You can name it however you want. And you hit command enter to save your results. So we use this function ls parenthesis to list all the objects that you have saved so far in your environment. So if you hit ls, So as you can see, all of these objects have been saved in the environment. So if you hit ls and then you do command enter, you're gonna see a list of all the objects that have been saved so far. You can also remove objects. So to do that, you just have to do rm, and you can choose to remove like A or B, however you want. In my case, I'm gonna remove A. And you're gonna see that A has completely disappeared from the environment. So we deleted it. You can also delete multiple objects at the same time. So you can do like, I want to delete A, I want to delete B and X. And when you hit command enter, you're gonna see that B and X have been deleted as well. So you can also choose to remove all objects. And to do that, you just have to do the RM. So RM stands for remove. And you make a list. And you be like ls, like this. So this basically means remove the list of everything. Because remember, ls shows everything that have been saved. So remove list of everything. So when you hit command enter, you're gonna see that everything has disappeared from the environment. So those are the cool things that you can do with R. So now let's talk about the classes or data types, the one that we saw yesterday. So R is a high-level programming language, and it works with objects that are characterized by their names and their contents, as well as their attributes. So these objects are constituted of basic types of elements, which are mainly known as data types. And there are 4 basic class types. We saw that there is integer, there is numeric, there is character, and there is logical. So let's first start to learn what is integer. So integers, remember, these are whole numbers. So any whole number is an integer, right? So let's assign another variable to be x. So since I've deleted everything, I can rename it x here. I can do x equals to 2. So I'm assigning my variable of x to be equal to 2. And to check the class, I can do class, and then you put in x, since R will already know x is equal to 2. So you put in x, just x. And then when you hit command enter, you're gonna see that this class right here is numeric, because remember, integers are part of numeric, because numerical values contain positive values, negative values, decimal values. So like it will automatically be numeric if you run it like that. So if you want your value to be an integer, you need to specify as such. And what I mean by that is just do x. So define x, you want your x to be an integer, and you use the function as dot integer, and you type in, you want your x to be an integer, right? So you type in x, and then when you hit command enter, you're gonna see that, so to verify if you've if your x has been like is an integer now, you can either look at the environment. So the 2L, the bigger L means that, oh, it's an integer, right? But you can also verify it by just using the function is.integer, and then type in your value, your variable. So in this case, x, and you can see that is x an integer? It's going to be true. You can also recheck the class now that you've specified that you want your x to be an integer. And you'll see that x now is an integer, okay? You can also check the value of x. So by simply doing x, or you can do print x, however you want. It's gonna take you to the same thing, okay? So now let's talk about numerical values. So numerical values, remember, these are either decimal values, positive values, negative, or whole numbers. So let's see another example. Let's name another n equals to 0.5. You do this, you're gonna see that n is equal to 0.5, and it's saved right here. So to check the type, let me actually change. So you can change this to grid, and it can give you the name of the variables. It can give you the type. It can give you how many elements you have, and the value of these elements and what are their sizes. So if you type n equals to 0.5, you'll see that n is saved as numeric. So if you want to check the class, again, you can just do a class of n. And then it'll show you that the class of n is numeric, and you can do like is dot numeric just to check if n is numeric. And if it's true, that means it's numeric. You can also do is dot integer n. So you're asking R like, is n an integer? And then you hit command enter, you're gonna see that is false, okay? Because it's a decimal point. So you can also do the same thing for n equals to 10. It will take you to the same process. Okay, now let's talk about the characters. So the characters are anything that you quote, like, so you need to quote them to make it a character. And these represent string values in R. So you can, we can do a quick example here. So I named it my character. So this is the name that I gave it. And I want my character. So you open the quotes. And you can, characters values can be like numbers, it can be letters, it can be words, so anything that you want, as long as they're in quotation marks, okay? So here I just wrote single cell, is amazing. And when you hit command enter, you'll automatically see that my character, which is what I named it, has a character type, and it has one value, which is single cell is amazing, okay? You can also, so like, it doesn't matter, it can either be double quotes or single quotes, so it'll take you to the same thing. We can do another example right here, so we can do this, and single quotes, nearly type in the same thing. And then when you hit command enter, you'll see that this also is saved as a character type, although it has single quotes. But there are a few things that you need to pay attention, okay? If you put double quotes inside of quotes, like that's gonna display an error. We can do a quick example so you see what I'm talking about. So if you name another variable called my character 3, and you do like, so single cell, it was amazing. And inside of it, let's put in some quotes. So I can just do this. So when I run this command, when I click command enter, you're gonna see that this is an arrow. It's gonna, like, R is gonna be confused because it's gonna think there are some quotes that you forgot to close. Okay, so if you really want to put this quote inside of it, all you have to do is just let R know that it's a special character. And to do that, you simply, I'm gonna show you, that was amazing. So if you want to put some quotes, just make sure that you put in a backslash, okay? So do this, just put a backslash before the quotes, and then when you run command enter, this is gonna be saved as a character type. So these tells are, okay, so this is a special character, like I shouldn't pay attention to this, okay? Like, and then it's gonna save it as a character type. Okay, so now let's talk about some logical, the logical type. So the logical type, data type is like contain the Boolean truth values. So it can either be true or false, okay? We can see a quick example here. So if you can name it however you want. I'm just assigning my variable to be named my logical. And I can simply do my logical. I want my logical to be false, right? To be equals to false. And when you hit command enter, you're gonna see that my logical is a logical data type and it has a value of false, okay? So it's false. And you can either do false, like in the whole word, or you can just type capital F. So it doesn't matter, okay? Just like this following example. So you can do my logical too. And you can type in T instead of true, okay? So we can type in T, and R is gonna know that, okay, so this is gonna be saved as a logical type and that has a true value. Okay, so we can, like I said, logical values are usually used via comparison between variables. So we can maybe do a quick example here. So I can assign my variable to be named W, right? So you can name it however you want. And then you hit Command Enter. You can assign your variable to be named Y, and then Y equals to 4, Command Enter. And I want to know, is W larger than Y, okay? So remember, if you want your results to be saved, you need to give it a name. And to do that, you need to assign the value to the variable. And to do that, so I want it to be named as Z, and I'm asking R, is W greater than Y? So when you hit Command Enter, you're gonna see that Z is false. And if you want to see the value of Z, you can simply type Z, the results. It's gonna display the results, and it's gonna be false because 1 is not greater than 4. Okay, so you can also choose another, is W less than Y, and then you hit Command Enter, you print the value of U, you're gonna see that this is true. Okay, so this is how you can use it. So now let's talk about the factors. So factors are seen as categorical variables. They are used when doing statistics or plots. And by categorical variables, I mean it has to be a category. So by a category, it can be like, so in this case, I chose a sex category, but it can also be like alphabet, it can be numbers, as long as it define a category, basically, okay? And I know it doesn't make sense to just put one thing right here, but you're gonna see when we put multiple variables together, it's gonna make more sense. So if you I've choose my name to be called my factor. And then, so to create a factor, one thing that you have to keep in mind, you have to use the as.factor function. Okay, so the as.factor function means that you're about to create a factor data type. Okay, and you open your parenthesis, and then you type in your categorical variable. Okay, so in this case, like I said, I choose a sex category, which is male, because there are males and females. And then when you hit Command Enter, you're gonna see that this is saved. So let's look for my factor. My factor is gonna be saved as a factor data type, and it has 1 level. So each category is gonna count as 1 level, okay? Okay, so now let's learn how to manipulate objects. So vectors, there are a collection of elements of same class, okay? So what I mean by that, remember, vectors are homogeneous, so they have to contain the same data type, right? So we can put a bunch of numeric values together. We can put a bunch of logical values together, as long as they're the same data type. And when you're doing that, you're creating a data type called a vector. And to create a vector, you need to use the combine function C. So this function right here is what, So this function right here is what you want to use if you want to create a vector, okay? So let's talk about, for example, and the function C, by the way, remember, I said it yesterday, it stands for concatenate. So maybe putting things together. If you want to remember it, it means putting things together, and you have to use this function C, but it has to be in the same data type. Okay, so we can create numeric vector. So let me name it just numeric vector so that we know. And so remember, to create a vector, you need to use the function C. So I use the function C, I open the parenthesis, and I just put in random numbers. So it can be two, like these are really random numbers. So feel free to put anything that you want. So if you do a numeric vector like this, you run it. Oh, so this is an arrow. So see right here. So this is an arrow because there is R is going to be confused. Like I put two comma, like it's going to be confused here. So let's do another. Let's correct this. So these are the things that you need to pay attention to. So you can do numeric vector like this. So do the function C. So R knows that you're about to create a vector. And then you can just put literally the same numbers. Just make sure you don't put two commas again. And then 5, and then run it. So now it's going to be saved as a numeric vector. And this thing, like these square brackets, basically tells you like, oh, you just created one vector, and this vector contains 5 elements, okay? And it shows you the 5 elements, so 2, 6, 3, 4, 5. Okay, so so these are the way you can create a numeric vector. So just put a bunch of numbers together and make sure that you use the function C. And to create a logical vector, so it's gonna work the same way. So just remember to name it logical vector. And then you use the function C to make sure that R knows, oh, you're about to create a vector. And I want my vector to be logical vector. So put in some true or false value. You can, and like I said, feel free to use whatever. You can basically write a capital F, or you can write true in whole words, or like you can write just F or T. So let's do the same example. You hit Command Enter. You're gonna see that this is saved as a logical, and this tells you, this square bracket here tells you that, oh, like this is a vector of 5 elements. You can also view it. So you can, like I said, see how I said, like, you can just print the value of X or a Z. So even here, by the way, if you see that R is suggesting these things right here, so you basically don't have to type the whole word. If you just click tab, R is gonna like know that you want to write the logical vector. So you don't need to write the whole thing. And that can save you a lot of time. And if you want to see the elements of this logical vector that we just created, just write in the how you named it. And then when you hit Command Enter, you're gonna see the list of all the values that you've created. Okay. So now let's talk about character values. So remember, character values have to be in double quotes or single quotes, and to basically create a vector of a character, all you need to do is to add the function C so that R knows that you're about to create a vector. So you basically you're gonna open your quotes, put in the value that you want, open another quote, put in the value that you want, and remember these can be numbers, they can be letters, they can be words, so whatever you want. So we can do this, it can be 10. Let's put in other words. Okay. So see, like I put in some, it can be like anything as long as it's in double quotes, okay? So when you hit Command Enter, you're gonna see that it's saved as a character type, and it has 6 elements, which are X, Y, Z, 27, 10, and my name is Laura. Okay, now let's talk about the factor vectors. So the factor vectors are the same way as you write the character vectors, okay? Because remember, even the factor vectors, you have to put in the quotes. But the only difference to specify that it's a factor, you need to use this function here. So as dot factor. So to create a factor right here, so all you need to do is literally like name it. So factor, vector, and then you have to give the s dot factor to the whole function. So that's what you're gonna start with. So you're telling R that you want to create a factor, okay? And you tell R, okay, I want my factor to be a vector. And then, so to do that, we use the C function, which is the combine function. And all you need to do is to make a list of what you want to do with, like which factors you want to create. So in this case, I chose letters, okay? So we type in the letters. Can type in the letters, E, and then when you hit Command Enter, so you're gonna see here that the factor vector has a factor type. It has 5 elements, which are A, B, C, D, E, and it has 5 levels. So each level is each category, like, is gonna count as not a category, like each. So like A, B, C, D, E is gonna count as a level, each one of them, okay? Because they are different. But if we choose to do this example right here, so let me just copy paste it. So if we choose to do this, so notice how this like has 3 B's inside, but it's still 5 elements. So if you run this, you're gonna see here that it has 5 elements, but it has 3 levels, okay? Because I told you that each letter is gonna count as a level. But in this case, these 3 letters are the same. So they're gonna be counted as 1 level, but it still have 5 elements. But these are like 3 levels because it's A, B, C. And these are A, B, C, D, E, so they're gonna be 5 levels. Okay. However, there are certain rules that need to be applied if you decide to mix different data types together in one vector. Because remember, vectors are homogeneous. So if you decide to mix data types together, there are certain rules that need to be applied. And those rules are like, if you mix logical data types and numerical data types together, it's going to be converted as numerical. Okay, we can do a quick example so you see how it looks. So I just name it logic underscore num underscore vector. So another thing that you need to take account is like, you can't name this like logic num like this. So you need to like put some things in between. I usually use the underscore. So just I'm naming it so that it's easier to understand. So the logic num vector, meaning I'm about to combine logical vector and numerical vector. So if you do this, remember, to create a vector, you need the function C, and I want my numeric vector my numerical value to be 1 and my logical value to be F, okay? F or false, however you want it. So when you hit Command Enter, you're gonna see that the logical and numerical vector that we combine together is converted into a numerical data type, okay? So it's a numeric now, and it's a numeric vector now. And basically, if you put in, because like, remember, it's gonna be converted into numerical, right? So the false is gonna be converted to a number. And if you put in false, the number is gonna be 0. And if you put in true, the number will be like 1. Okay, we can do the same example. So you see what I'm talking about. So let's just do vector 1 here, and we can create 1. Now I'm doing true instead of false. So remember, if you mix logical and numerical, it's going to be converted to numerical. So meaning that this logical value here has to be a number now. So if it's false, it's going to be 0. And if it's true, it will be converted to 1. Okay, so now in the case where you're mixing logical, so logic, numerical, and character values, okay, in one vector, And to make it a vector, open the C function, and 2 is gonna count as my numerical values, true is gonna count as my logical value, and to make it a character, I need to code it. So if I do this, you're gonna see that, 1 second. Logical, yeah, so it's this one right here. So logic, numerical, so this is how I named it. So it becomes automatically a character type. So it's gonna treat, all of these things are gonna be treated as character. And remember, characters can be numbers, they can be letters, they can be anything. So like here, like instead of just putting 2 without the codes, it just put 2 inside the codes just to make it a character. Okay. So now let's talk about, I'm sorry, does anyone has any questions so far? For some reason, I can't open the chat.
I don't see any questions coming through,
Okay.
Sarah, but maybe we should give it a minute or so for people to type, should they be asking questions via chat.
Okay, great.
And also, if you would like to ask your question verbally, you should feel free to unmute yourself and ask questions.
Yeah.
Sarah, there is a question here. Can you make a specific element numeric in the character vector?
Can you make a specific number? Can you repeat?
Sure. Can you make a specific element numeric in the character vector?
Yes. So that's, so a character can, so you can make like, yeah, you can put, you mean like you can put new numbers into like a character vector? Is that what you mean?
Maybe Zacchaeus, if you're comfortable, unmute yourself and ask that way, or continue communicating over the chat.
I'm not sure what you mean, Zadia, but like if you mean that if you can like let me do this. So to make a vector, you do this. So you mean like, can you put numbers inside of a character vector? I'm not sure. Because yeah, you can, but you just need to code it. And if you mean that, if you mean like, can you combine a numeric vector into a character vector? Like, that was what I was talking about. We can do like an example so you see. So you can do X.
Hi, Sarah.
Hi, Zacchaeus. Yeah, so are you able to speak?
Yes, because I am noticing in your character vector, there are numbers there, as well as some letters as well. So if you wanted to preserve the numbers to remain numeric, would it be possible to do so?
Yes, so if you want your numbers to be numeric, if you want to create, so remember vectors, they're made as, it has to be homogeneous, meaning that it has to be from the same data type. So you cannot like mix character and like numeric. And if you do that, there are certain rules that have to be applied. So like one is gonna convert into another one, like because vectors are like basically they come from the same data type. Yeah, they can only hold data of only one type. And remember, to create numeric vector, you just put in numbers, okay, without any codes.
All right. No,
Yeah,
that's clear now, because I was looking in the context of a data frame where the columns are the vectors. So which means you can change any other column into whatever data type you want, but still retain the other ones as another data type, isn't it?
So data frames are different.
Okay.
We're gonna get to that later, and I'm gonna show like how it works. So for a data frame, you use vectors. They have like they have to be, so the elements in those vectors have to be at the, like, they have to contain the same amount of elements.
Okay.
Yeah, we're gonna get to that and you'll see what I mean.
All right. No, thanks.
Yeah. Okay. Does anybody has any questions so far?
I do believe there's another question from Akiko. Akiko, do you want to unmute yourself and ask it, or would you like me to ask it on your behalf?
Yes, sorry, I'm still confused about the vector function, like C bracket 2T X. So like you said, the vectors should be homogeneous, but the number and its logic and letters, it's not homogeneous. So I'm a little bit confused about vectors, and then whether you can
Okay.
put like those like a different numbers, letters. Yeah.
Okay, yeah. So let's go back to remember we defined that there are some basic data types, okay? By integer, this is one data type. This is another data type, numeric. Character is another data type. Logical is another data type, right? So to define numerics, so numeric mean basically it's numbers, okay? Numerics are only numbers, right? And characters, they can basically, the way you can think about it, characters, you need to give it a quote to tell R. So you need to double quote it or like use single quotes to tell R that you're about to create a character, which is what we did here. So a character can also be numbers. So if we do like, so let's do another example right here. So if you do, let's just call it character. So this is just a name. I'm just giving it a name, character 1. It can also be a number. So you can just, as long as it's in double quotes, this is gonna be a character, okay? So if you run it, you're gonna see that character 1, which is what we just named it, has a character type and it has a value which is like 1. So this is a character because it's in double quotes, okay? And a vector simply means that you can combine a bunch of characters together. And if you do that, these are called character vector. So if you put a bunch of character values together, it's gonna be converted to like a character vector. And if you put a bunch of numbers together, so you need to this is why we use this function right here, which is the C function, the combine function. So C stands here for concatenate, meaning putting things together. So here we're trying to put numbers together, like a list of just random numbers. And it's going to be saved. So we already run the code. So if you look for a numeric vector, it's going to be saved as a numeric type. And to tell that it's a vector, it has to be in square brackets, just like this. So this simply means that you just created a vector, and this vector contains 5 elements, which are 2, 6, 3, 4, 5. Okay, and if you decide to put a bunch of characters together, so you can simply like use the function C. So to make a vector, so a vector, like that means you're combining a bunch of one data type together. Okay, so in this case, we're choosing characters. So we're combining a bunch of characters together. And all you have to remember is to double quote it. So if I'm double quoting 27, it's no longer a numeric, it's a character because it's in double quotes. And you can just put like random things. As long as it's in double quotes, R is gonna know that it's a character, and the function C is gonna tell R that, oh, she's combining all of that, and it's gonna be a character vector. However, for factor vectors, so factor vectors are basically the same way as character vectors, but all you need to do to make it a factor, you need to add the as.factor. So this is the function that you need to add before to make it like to tell R, okay, I'm about to make a factor vector. And this function C means that it's a vector, okay? And the only difference here, like with character, remember characters, you just put random things inside of it, as long as you double code it. But for factor vector, it needs to mean that it's a category of something. So in this case, I chose letters, right? So letters, like I chose like alphabets, right? So there is A, there is B, there is C, there is D, there is E. So each letter here is gonna count as a level. So here there's gonna be 1, 2, 3, 4, 5 levels. So these 5 levels have 5 elements and it's a factor vector. However, here, as you can see, there is 5 elements still. So there is 1, 2, 3, 4, 5, right? But these B's are repeated 3 times, or repeated twice, I'm sorry. So like, since it's a factor, I told you like, in this case, I chose alphabets. This is gonna be 3 levels because there's only 3 letters here, 3 alphabets, 3 types of alphabets. There is A, there is B, there is C, but there is 5 elements. Does that make sense?
Yes. Can I ask you something about factor vector? Is it
Yeah.
possible to, for example, put 1, 2, 3, 4 and A, something like that as a category?
But like in that case,
Mm.
think about like, what would you want like your category to be?
For
'Cause
example,
that is-
A could be like absent, and then 1 to 3 is like the degree of pain or something
I'm not
as a
sure.
category. Yeah.
I'm not sure. Like,
As
because
long as
if
I
you
have, yes, double quotation, like
that means like I'm a little worried that R will be confused that it's a character vector instead of this one here.
oh, okay.
These are like these are alphabets. Like R knows that
Yes.
these are alphabets, right? So if you mix alphabets and numbers, like R is going to be confused. So make sure your factor means like this is a category of something.
Okay, thank you.
Yeah, yeah. Does anyone has any other question?
I think there's a question from Tina. Can you please repeat or go over the difference between a B/N integer and numeric?
A B/N? What
I
do you
think it
mean
just
by-
means between,
Ah,
like the difference
between.
between integer and number.
Thank you. As you can tell, I am not a computational scientist.
So the difference between what and what? I'm sorry.
An integer and a numeric.
Oh, okay. So integers are like whole numbers, right? It can be like by whole numbers, I mean, yeah, it can be like, so integers can be like all the positive numbers, basically, as long as they're not decimal points, okay? As long as they're like not decimal values. And numerics contain decimal values, positive values. So like a numeric here can just be like, let me name it S. So it can literally like be -1. This is gonna be numeric. So if you look here, it's gonna be numeric. So numeric can either be negative values, it can be positive values right here like this, it can be decimal values, and even integers, since I say that integers are whole numbers, so any whole number is an integer, so is part of numeric. So this is why I told you how like, so if you run this, X like this, it's going to be numeric, right? So if you want to make it an integer, you need to specify as such. So what I mean by that, you basically use this function right here. So you need to tell R, I need my X to be an integer, okay? And to do that, you basically use this function here as .integer. So you're telling R, hey, I know that by default, 2 is gonna be converted to a numeric, but I want my 2 to be an integer, right? And then you just hit Command Enter, and you'll see that 2 has been converted to an integer. You can either double check. So as .integer is to tell R, I want my X to be an integer. Is.integer is to tell R, is to ask R, is X an integer? So if you run it, you can see that this is true. And if you try to do like is dot, in this case, you wanna, one second. So if you decide to do like is dot, I want to ask R, is X numeric now? Now that I've specified that I want it to be like an integer. So you can ask R like is X a numeric, and then it's gonna be true, but you've already assigned it to be an integer, and it's basically gonna be saved as an integer. Okay, does that make sense, or do you need another example? Does that make sense?
Sarah, are you able to see the chat, or do you want me to read off?
No, I can't see the chat for
Okay,
some reason.
So Tina did follow up saying, thanks for the clarification. So why did the value change to 2L?
Oh, so this is so when it's an integer, you're gonna see 2 and L. I can do another example so you can see like whatever you put in, like this is just to tell you like the 2 capital L, any integer that you're gonna define, it's gonna be a capital L besides it, basically. I can just do I don't know, let's do H like this. Like 20, right? So H is numeric. So it's going to be converted to numeric. And if you want to assign it as an integer, just use the function as dot integer, and then put in what integer, like what variable you want to do the integer. And then when you click like this, you're going to see that H is now an integer and the value is 20. So the capital L basically means that it's an integer now. It's gonna come like that. This is just by default by R to tell you that it's an integer. Does that make sense?
I think Tina is saying that it does. You have another question from Monica asking what scenario would require the number to be an integer?
It's really up to you. Like it's like it depends with what you want to do, right? So some people just want to like all their numbers to be like integers. They don't want to see like numbers, because remember you can also remove things. So you can use like these type of things to remove any number and and you want like all the integers to remain. So you can just assign the values that you want to be like your values that you want to be like converted to integers, and you can just remain with those values if you don't want to mix up like numbers and integers. I guess it can be used in that case.
Okay, Monica says that makes sense. So I don't see any more questions, Sarah. So I think you're probably free to continue on with the lecture.
Okay, great. Thank you. Thank you for your help. Okay, now let's talk about the list. So the list can literally be anything, right? So see how like I was telling you how the vectors can only contain one data type. So list is totally like the opposite. List is non-homogeneous. You can mix anything in the list. So list can be numeric vectors, they can be logical vectors, they can be numbers, they can be, you can even put a function inside of the list. You can put another list inside of a list. So let's see like some example here. So let's recall what is numeric vector tab. So these are the values that are inside numeric, okay? Logical vector Okay, and then character, vector, hit command enter. So these are the values. I'm just doing this so that you don't get confused in the list that I'm creating here. So to create a list, we use the function list and parentheses. And what I mean by that is clearly, so you first have to assign it a name. Like I want to call it my list. So I use the assignment operator to create my name, and you basically use this function, so list and parentheses. This is how you create a list, right? And then you put in whatever that you want to create. So I want to include my numeric vector, which contain a bunch of number. I want to include my logical vector, which contain a bunch of logical values. I want to include the character vector, the ones that I made before, right? So I'll just have to copy, let me just copy, paste, right? So when I run it, 1 second. Okay, so this is an error because see, like I forgot to put the numeric vector because I defined it as numeric vector. So I need to specify as such, otherwise it'll be an error. So I'm just gonna literally copy the same thing. Just make sure to add the numeric. So these data types right here, I've already defined them. I just want a list of all of these vectors, right? So I click command enter, and let's look, we called it my list. So let's look for my list right here. So you're gonna see that it's saved as my list and has a list type. And inside of this list type, there are 3 elements, which are numeric vector, logical vector, and character vector. So you can also click on this magnifying. So if you do this, you'll see that it's going to give you the list of those 3 elements that were listed. So these are like, this is for numeric vector, and basically the double means it's by default. It also means numbers. So numeric is you're gonna see that a lot if you're using R. So like you see that here, like the numeric vector contain a list of 5 elements. The logical vector contain a list of 5 elements as well. And then the character has 6 elements, right? And I think, yeah, and you can also view it, like if you click on this, you can be like, oh, I want to see my list in the character, right? And then when you hit command enter, you see the list here listed, and it's 6 elements. So let's see another example to make sure that you guys understood. Let's call it my list 1. And to create a list, remember, you need to use this function right here, the list and the brackets. So we can literally put in the same thing that we just put in, right? Just to gain some time. And you can put numbers, just random numbers. I can do like 89. Right? You can put a list inside of another list. So I can really put the same thing that I was putting. So 1 second. So I just included another list inside of this list right here, right? And you can add a function. So let me add the function, the mean function, right? And then let's do command enter. So when you do command enter, you'll see that my list 1 has been created. It has a list of 7 elements. And if you click on this magnifying glass right here, it's gonna take you to this page. So you're gonna see a list of 7 different different elements. And each element, it also tells you like what those what does each element contain? What does like basically like this double, which is numeric, which is a numeric vector, what does it contain? So it gives you a list of each one of them, like what is it in there, right? So the logical has these values right here, the character has these values right here. This is double, so number, it has this value right here. This is another number that we added inside of the list. We are also added another list inside of the list. So it gives you that this is a list of 3 elements. You can also check it and then do this, and then it's gonna show you what is included inside of this one here. You can also, I believe, click this, and then it can show you like what is inside of the list that you created inside of the list right here, right? So it can show you this. You can also, this is the function that we added inside of the list. So in the list, you can basically add anything. It's just a list. It can be nearly anything. You can add vectors, you can add numbers, you can add anything that you would like to add. Does that make sense, or does anybody has any question? Okay. So for data frames basically the way that you would think about it, it's a list of vectors that these vectors have to have the equal length. So by equal length, what I mean by that, so first of all, to create a data frame, you can do my data frame. So this is just the number that I'm assigning, and you can do data dot frame. So you use this function right here to create a data frame. And data frame is basically a list of vectors, but these vectors have to be equal length, okay? So let's see an example right here. So let's do, let's include, remember they need to be vectors, but these vectors have to have the same length. So let's put numeric vector and let's add logical vector as well. So when you hit Command Enter, you're going to see that a data frame has been created, okay? And you can click on this tab right here, and then it's going to bring you here. Okay, so by length, I mean they have to have the same amount of elements, okay? So it's gonna say like, okay, the 2 is gonna be false. I want my 2 to be false. I want my 6 to be false. I want my 3 to be true. So like if you can recall, the numeric vector has 5 elements, and the logical vector also has 5 elements. Let's recall. Right? So let's see the character vector. Let's see how many elements are in there. 1 second. Character vector. So this has 6 elements, right? So let's try to create a data frame, but with using different elements different vectors that don't have this the equal length of vector, equal length. Okay, so let's name it my data frame 1, and instead of logical vector, let's name it character. Let's use the character vector. So yeah, so when you try to do this, it's gonna say that it's an error, right? Because like it's gonna tell you one has 5 elements, the other has 6 elements. So you cannot, therefore you cannot create a data frame, because remember, a data frame has to be a list of vectors of equal length. So I don't know if that makes sense, or you need another example. So like this right here worked because numeric vector and logical vector, they both have 5 elements in each of them. So this is why it worked. Okay. Okay, so you can also like assign them, you can like label them. You can be like, okay, I want my numeric vector to be labeled as X, and I want my logical vector to be labeled as Y. So when you do that, you hit Command Enter, go to your environment to see how it's saved. So I named it as my data frame 2, and then you go to this tab right here. So when you click on it, you're gonna see that the X, which is numeric vector, is gonna be named X here. And then the logical vector is gonna be named Y here. So these are the kind of things that you can do to just kind of organize your data and yeah, know where things are. Okay, now let's talk about the metrics. So metrics are like basically same as a vector, but you need to, because when I mean same as vector is because to create a vector, it have to be the same data type. So with matrix, it's also the same. It has to constitute one data type, but all you need to add is how many rows do you want and how many columns do you want. So you need to add the numbers, right? So let's basically remember we've already created this character vector, which is right here. So we've already defined it and it's saved right here. So when we run it, R is gonna know that we're referring to the character vector that we've already run before. So to create a matrix, you basically use this function right here, which is matrix. And all you need to do is, basically you specify the data type that you want to include, and you just add the n row and the n column. So let's do it so you guys can see. So I assigned it. I want my matrix to be named like this. So matrix, and when you hit tab, so it's even gonna show you. So the first thing you need to add is data. So what is the data type that you want to do? And what is the number of rows that you want? And what is how many columns do you want? Okay, so in this case, we want our data to be character vector. You hit tab, and you can do my n row. So now you need to define your n row that you want. So I want 2 rows and I want 2 columns to be equal to 3, for example. So when you run this line right here, go to the environment, look for my matrix, because this is how we saved it, and click on this tab right here. It's gonna bring you to this page, and you can see that we've created 2 rows and 3 columns in this character vector that we have. So yeah, this is how you create a matrix. And to create a data frame, remember it has to have you can create like a list of vectors, so it can be like multiple lists of things, but make sure that inside of those lists, make sure that the length is equal, because you're basically telling, oh, this 2 is because x is equal to 2 corresponds to false. Okay, 6 is correspond to false. So it needs to be like aligned like that. But for matrix is like you just define the data type that you want to do. Remember, you can only do one data type, like only one data type, and you just define the number of rows that you want and the number of columns that you want to do. Okay, and please let me know if anyone has any question. Okay, so for indexing, the first thing that we can index are like vectors, and vectors are in one dimension. So what I mean by that, indexing basically help us to access value of an object easily, right? So let's say we want to see the value of the logical vector. So remember, we've already created a logical vector. So these are the values inside of a logical vector. So, and then we want to see, okay, so what is the second value, right? What is the second value inside of the logical vector that we've created? And it's gonna show you that second value, it's false. So as you can see here, the second value is false, okay? You can also use, you can just be like, okay, I want you to list so we've defined character vector. So, okay, I want you to list the first 6 elements. So all you have to do is, okay, I want my, from element 1 to element 6. So you do column and then you hit 6. So when you do command enter, you're gonna see a list of the first 6 elements, right? We can also, and feel free to change it, by the way, however you want it. You can also remove values, values that you want. And to do that, we can so let's type the logical vector. So make sure you use the square brackets if you want to access the value through indexing, okay? So you use the square brackets, and I want to remove basically the first value among the logical vector values that I've created. And when you hit command enter, you're gonna see that, remember, the logical vector values were false, false, true, false. So you're gonna see that it's false, true, false, true. So we've removed the first value in this case. Okay, now let's talk about the function. So to define a function, so you first have to assign it a name, just like we did it before, using the assignment operator. And we use this function to literally create a function. This is how you create a function, right? So all you need to do is basically, I think I put in, so this is like the template. So you tell it how your function, you want to name it, right? So if you want to name it, I don't know, function 1, like however you would like to name it. And then A is going to be value 1, B is going to be value 2, and you can do like your results. What do you want your result to be? Like, so what do you want to do with this function right now? Okay, so now that you've told us that you want A to be the value 1 and B to be the value 2. So now what do you want to do with value 1 and value 2? And to do that, you go to the next line and you tell it, okay, I want my results to be equal to value 1 plus value 2. So it's gonna use the sum function, right? And then you do return. Return basically means enter the results, right? And then, so we can do an example here. So since we've already created, right? So we've created this function, we've already created it, right? So let me see. So let's run this, right? And so this is how we define a function. So I want my function to be named new function. And I'm using the function, this function to literally create a function. And this is where I'm going to put the value 1. This is where I'm going to put the value 2. And the way that I defined it, I open the accolade right here. And I want my results to be like value 1 plus value 2. And when you run it, that means you've created this function. Okay, so now define what you want these values to be, right? So you can simply do, so the function that I created, which is named new function, right? I want my value 1 to be 15, and I want my value 2 to be 20, right? So when you hit command enter, you're gonna see that 15 plus 20 is 35. Is there any question?
Sarah, you do have a question. Please, can you go through indexing?
Yeah, sure. So indexing are a way to access the value of like an object easily, right? So let's do another example right here. So okay, let's use numeric vectors, right? So I'm using vectors because that's how you create a bunch of things together, right? So let's do like numeric vectors, and we want to see the list of, so what do you want to see? I want to see like a list from 1 to 4. It's gonna show you the list from the first element to the 4th element. And I'm like, okay, so let me remove the second element, for example, right? So there's 2, so it showed me the first 4 elements. Okay, let me remove the second elements now. So all I need to do is type in the data type that I want to use, right? And open the square brackets. So for indexing, you have to use the square brackets. And then all you need to do is remove, and we do a minus sign, and then 2, and you hit Command Enter. You're gonna see that the second element has disappeared. Does that make sense? It's basically a way of accessing the values like easily, without like, you can just be interested in seeing like the first 5 elements, the first 2 elements, and then see what you want to play, how you want to play with it.
So I don't see any other questions coming through. We are running 10 minutes over time, Sarah, so I don't,
Okay.
are you close to ending the lecture?
Yes.
Okay, so maybe we
Yep.
should wrap up this and then we'll take maybe a 10-minute break instead of a 15-minute break, and make up time that way. So I'll let
Okay. Yeah.
you end it.
Okay. So next thing that we're gonna see is like how to install a package, right? So to install a package in R, all you have to do is install .packages, and then you open this bracket here, you type in the name of your function, and then it's gonna install itself, right? And to load the package, you basically do library, and then you put in the name of the package. And then to see a list of all installed packages, you can simply hit library. And then when you run this line, it's going to show you a list of all these installed packages. And then to get help, all you need to do is you can do help equals the name of the function that you want to get help with, and you can do it. And it's going to show you, so like this. It's going to show you all the details about the ggplot2 function and everything, how to use it, right? And then, so another way of getting help is like, just type the name, like these are the 3 ways you can get help. So type the name of the function inside of it, or put a question mark before the function, or you can also get an example by doing example and then put the name of the function inside the quotes. And then if you want to read the data in a file, the first thing that you need to do, if you don't know where you are right now, you can just click get working directory, and then it's going to show you where you are. And to set the working directory, all you need to do is to, you can basically go here to files, and then you can maybe create a new folder, call it data. So this is where you want like all your data to be saved when you set your working directory. And then when you create it, you go like this, you do more, set as working directory. So that's how you will do it. Okay. And then if you want to import some files, and you can do it by like such as Excel files, you can just do it by red.csv, just indicate the path to the file name and make sure that it's .csv, okay? If you want to read some text file, just import them and put them into red.dlm, and then include the path file and make sure that it's .tsv. Okay, so now let's quickly see an example of how the plot works. Okay, so let's load the ggplot2. And basically, the ggplot2 is a plotting package. It allows us to graph most kinds of data in a simple way. And the first thing that you have to do, if you don't remember, you can just hit help, or do a question mark ggplot2 to see how to use this function right here, right? And then the first thing that you need to do when you're using the ggplot2 is like you can do data like this to view all the R data set. And then it's going to show you a list of the data sets that are included inside of R, right? And once you've chosen your data set, you can just load the data. So you can do data, and you've loaded the data. And then once you've chosen your data set, all you have to do is to define an aesthetic mapping. In other words, you have to specify your axes and name them, right? So if you do like BOD which is the biochemical oxygen demand, it's going to show you what is inside of this data type. So choose your mapping, so label your axis. So until now, you're not going to see any plots until you add the geom layers. And the geom layers represent, they're basically used to represent graphics of the data in the plot. And there exist many geoms. So there is geom points, which are for dots, scatter plots, etc. There are geom line, which are for time series, trend line, etc. There are like for box plots. So you can use these different geom points. And if you're not sure how they work, you can just simply use the help tab and type them in. So let's see a quickly example and close this since we're out of time. So I am naming my BOD to be named by chem oxygen demand, and I want to create a ggplot. So I want my data to be equal to BOD because this is how it's called here. And then I want my X to be equal to time and my Y to be equal to demand. So to draw the plots, so we've already defined all of this. So this whole thing is going to be equal to biochem oxygen demand, right? So to draw the plots, you can simply do this. Because remember, you can simply do this and then add a geom point. So you need to add a layer to see a plot, right? So when you see this, so remember geom points are for like dot plots, scatter plots. So when you do this, 1 second. Not found. We can just do like this. Let's just add another layer. And we can do geom point. And then do this. Okay. And then we can basically choose the size. I can be like, oh, I want my size to be equal to 10. And I can add another layer. And I want my geom line to be equal to, I can define the color to be red. Where is it? Interesting. I don't know why it's not running. Let me share my screen on my RStudio on my computer to see what I mean by that. 1 second. Okay. So what I mean by that is basically make sure that you've loaded your package right here. So do data like this, data like it's gonna show you a list, load the package, load the data sets. And so when you run this ggplot, it's not gonna show anything, right? So for it to actually do the plot, you need to assign like, you need to add the layers basically. And all you need to do when you run them, okay, oh, you need to run this first, right? So you run it, and then you can do geom this, and then you can choose your size. And then you can see this figure right here. You can also change you can also do different size. So if you do this, you can see like the size has changed. So like, yeah, I just wanted you guys to see the difference. So you just have to, just to recapitulate, you need to do the data, define your aesthetic mapping, and then add geom points, and you can add different geom. You can add the geom point, you can add the geom line, you can even label the title, and you can do like a bunch of things. But right now we're out of time, so I'm just gonna close this now.
Thank you, Sarah.
So let me know if you can see my screen.
I can, it's, you just need to put it in presenter mode, Daniel. There you go,
Okay.
perfect.
Okay. So my name is Daniel. I'm working currently at the Claremont Cell Observatory at the Broad Institute. My background is in computer science, and I'm going to talk to you today about pre-processing and quality control of single-cell RNA-seq data. If you have any questions at any point, please send it over on the chat, and Christine can maybe let me know. And we have time at the end too, so I can answer questions at that point as well. So feel free to interrupt me at any point. What we're going to discuss today is, first, we're going to go over the steps that we need to go from raw sequencing files to count matrices. So, and then I'm going to give you a demo of Terra, which is one of the tools we use to orchestrate all of these pre-processing steps. And then we're going to discuss quality control and normalization. Okay, so raw sequencing files to count matrices. So we ended the first lecture of yesterday, if you remember, about the different RNA-seq methods. The overview that we got would usually end at the sequencing step. So there's a lot of wet lab work that goes into collecting the cell sample, preparing the library, and then it's shipped off to these magical sequencers, which sequence the RNA in our cells and output that sequence. So after this, after we have this sequencing file, we need to convert it into the gene by cell count matrix that we are going to work with. So I don't know if people are familiar with that, but usually our actual analysis starts with the cell by gene count matrix. We'll see that in depth later if you're not familiar with it. But so I'm just going to give you a high level overview of what the steps are to go from the raw sequencing output, so the ATGC output that the sequencer spits out, until we get the count matrix, which is like for each cell, for each gene, you have X number of reads. So how do we get from here to there? So there are a few steps. So the first step is to go from BCL to FASTQ. So BCL is the file format that is generated by the sequencing machines. So you can see here, I don't know if you can see my laser, but so the sequencing will output BCL files. So multiple libraries can be pulled together and run on the sequencing file, and one BCL folder as output. So the first step is to convert BCLs to FASTQ. So just to give you an idea of what a FASTQ file is, this is the file we're going to mostly be interacting with, especially if you're like looking at other people's research papers. They'll usually make FASTQ files available for download so that you can use their data as well. So a FASTQ file is a set of read sequences. So there's going to be 4 lines for each sequence, and there will be like, you know, 1 million of these sets of 4 lines. So so the first line is just an identifier with some information about the cell. For instance, this cell barcode is GGT-CCA, and some information about the UMI, which is here CCCT. And it's just an identifier of this read. So this read has this identifier, that's all it is. And the second line is the actual sequence, so the actual bases. So this read is A, G, G, and so on. So that's the second line. The third line is just a separator, doesn't have any meaning really. And the final line is the base quality scores. So for each corresponding base call, so for this A call, we have this quality score. So it's in characters, but it's actually encoding some number. So this @ symbol corresponds to, let's say, 50 or something like that. You can just convert it using a tool that converts ASCII to digits. And then this will tell you about the quality of this read here. So that's what a FASTQ is. And this is like a universally shareable format of storing read sequences. And yeah, so the first step is to convert the output of the sequencers into this FASTQ universally shareable format. And we use CellRanger, MKFASTQ, BCL to FASTQ, or BCL convert softwares in order to accomplish this. I'll show you CellRanger MKFASTQ specifically a little later in the Terra demo. But yeah, so this is the first step. If someone gives you a BCL, you first need to convert it to FASTQ. So the second step, once we have our sequences, so we have like 1 million of these, we want to know which gene each read came from. So this step we call alignment to reference genome. So we have the reads, individual reads, and we want to align them to a reference genome. So we have people have compiled reference genomes for different organisms. And so, for instance, we have a human reference genome called GRCH38 that contains the sequence of human chromosomes, all human chromosomes, like a reference human chromosome. So like all genes, all sequences in a human chromosome have been collated and provided to us as this GRCH38 human reference. And so if we do a single cell RNA-seq of human cells, we will try to map those reads back to this reference in order to know which gene that read came from. And so this is called alignment. And we talked yesterday, there were some questions about which alignment to use. And it's kind of a matter of personal preference. But I think one of the questions was, are there any free aligners? And as I mentioned yesterday, all the softwares are actually free. I don't think any of them would ask you to actually pay, but running them actually takes a lot of compute and memory resources. And so it's a lot of times very difficult, for instance, to run STAR on your personal computer. It will take forever and probably will crush your computer and not finish. But there are some like Callisto and Sailfish that are, they're called pseudo aligners. So they have a different way of doing the alignment. So you'd have to actually do more research into it, but it is possible to run these in a local machine. So it's one option. You should consider a lot of different things when you're trying to determine which aligner to use. But one recommendation is it is mostly better to use a splice-aware aligner. What this means is if the reads come from a gene that is spliced, and so a portion of the gene of the sequence is removed before the mRNA is created, and some aligners are able to align a read across splices, and others are not able to do that. So most animal genomes are very have a high rate of splicing, and so it is recommended to use a splice-aware aligner. the 10x arrangers default aligner, which is star, is a splice aware aligner. So if other concerns are not there, like if there are no other considerations, I think star aligner is a good choice of aligner to use. And it comes as a default with this arranger count workflow. So makes things easier to use. So if you don't have any other constraints, I think star is a good way to go. Yeah, so once we align our reads, so now we know which gene each read comes from. What we are going to do next is just do counting. So what this means is we're going to go, we're going to build this cell by gene matrix by doing two things, the two main things, cell barcode demultiplexing and UMI deduplication. So cell barcode demultiplexing just means, so in the FASTQs we saw here, right? So we had a cell barcode. So each cell has a unique barcode attached. So each read that comes from a unique cell has a unique barcode attached to it. So this sequence identifies this cell. And so we're going to collect all reads from this cell and count them as belonging to that cell. And UMI deduplication means, so UMI is unique molecular identifier. During the sequencing process, there is an amplification process where in order to get better signal, we amplify each sequence, and that might give us falsely inflated counts, but these UMIs, which are attached to the read before amplification, will help us keep track of the unique molecules so that we don't read duplicate, so that we don't have read duplicates. So deduplication just means if two sequences have the same UMI, just count them as one.
So Daniel, you have a question.
Okay.
Hope it's okay to interrupt.
Yeah.
Can you give an example of a splice aware aligner?
Okay. Yeah, I think yeah, that question came before I addressed it, I guess, because here star aligner is a splice aware aligner. So if you're using star, the default 10x arranger aligner, then it is a splice aware aligner. So I'm not sure the status of each of these aligners, whether they're splice aware or not. I would assume Callisto maybe not splice aware. Don't quote me on that though. Like I can share with you resources in the resources Slack about details about each aligner, the pros and cons comparisons, and details about splice aware versus not. Yeah. So back to this. So yeah, so once we do our counting, we're left with this cell by gene matrix, which is the starting point for all our downstream analysis. So this should be very familiar to you. The way we read this is like for cell 1, gene 1, we have 3 reads. So there are 3 genes, 3 copies of RNA that come from gene 1 in cell 1. So it's very straightforward, and this is what we'll be working with in the lab and in your own analysis. Okay, so I'm going to go out of my slides for a second. So I'm going to talk to you about Terra. I don't know if people have heard about Terra. It's kind of an interface to cloud resources. So we mostly use Terra to do all of these pre-processing steps. And so I want to introduce you to Terra quickly. So this is the Terra interface. So you'll mostly have a workspace, and you'll have a set of workflows. So going to give you a quick demo of the Cell Ranger workflow. So Cell Ranger, like I mentioned, it's a 10x product, and it does both BCL to FASTQ conversion and alignment, and then counting. So make FASTQ and count, they're called, it has two workflows, make FASTQ and count. And so we'll go through, we'll run make FASTQ and count on each of our the BCL files that come into the lab, and we'll be left with that count matrix. So I hope everyone is able to see my Terra screen. I'm just going to show you one example. So this is the Cell Ranger run that we did for some projects. And basically what's going to happen is it's going to work with Google Cloud on the back end. I think other backends are also supported, like Microsoft Azure, but basically it's going to submit these jobs. So the FASTQ creation job, counting job will be submitted to Google Cloud Compute clusters. They'll be processed, and the data will be output to Google Cloud buckets. So really, once you set up these workflows, it's really as simple as pressing this run analysis. All we do is like we provide some inputs. So like this is a sample input that we provide. We push our BCL folder, the exact folder that was.
So Daniel, we see your slide, not your Terra application.
Okay.
So just bear with us, folks.
How about now?
Yes, I see a bunch of code. Yeah. Mhm.
Okay, awesome. Okay, just going back. So this is the Terra interface. We have workflows, and I was just mentioning that, yeah, so the inputs to our Terra workspace is this. Our workflow is the raw BCL file and the indices that were used to run the sequencing, and the reference that will be used. So this is the GRCH38 reference that I mentioned earlier. So once you have created this, yeah, it's as simple as just pressing run analysis, and all of the steps are automated so that your output will be pushed into Google Cloud. And yeah, Google Cloud buckets. So you can control a lot of the parameters, you can provide different inputs, and you can be as hands-on or hands-off as you desire. But it's really helpful, especially if you have a lot of data that you need to process, to use an automated approach like this. So another useful thing I wanted to show you is, so this is an example output of a Cell Ranger count result. So this is a very common, commonly seen folder in our day-to-day work. So we will have, first, I want to show you the web summary. So I've downloaded that here. So this is the result of one sequencing run. It summarizes the results. First, you have the number of cells, the mean reads per cell, the median genes per cell. So all of these are useful informations to have. So like if you tried to sequence 10,000 cell and get 5,000 cell, you could immediately flag that. It will give you information about, again, the sequencing depth and median genes per cell. So these are important information to look at. So you'll get that in the as part of the Cell Ranger output, the web summary file. It also, Cell Ranger flags a lot of quality issues, potential quality issues for you. So this is another example where the fraction of reads in the cell is less than the target of at least 70%, and so that is flagged. So this is a very good place to start your analysis / QC on, just looking at this summary file. Another important figure that is automatically generated for you by SciRanger is this barcode rank plot. So what this is doing is it's ordering, so barcodes are those cell identifiers that I showed you in the FASTQ file. So we are ordering them by the number of UMI counts. So you can imagine this as being just cell. So for each, we're ranking the cells by the number of unique RNA reads that have been collected from them. And so if you look at this, there are, so this is on a log scale, but basically there are like 3 type of sections. So this one, SciRanger has its own like cell calling algorithm. So it will tell you which barcodes are actually cells and which are either empty or background noise. So these are mostly, so this hill that you see is background counts. So these are just, it does have reads. So there are like, let's say 100 genes in this, in the cell that is here, but those are mostly, according to SciRanger, coming from like the cell soup, so free floating RNA. They're not actually encapsulated in a cell. So that's what this figure is telling us. Yeah, and the rest, which have like all almost 0, are just like empty barcodes. Okay, so important first step in analysis is to view this summary file. And the other one is this filtered feature BC matrix, which is the count matrix back in our slide, this count matrix in H5 format, and we'll see how to work with that as well. Okay, so yeah, back to the slides. So that's Terra, and Or mentioned it yesterday. We actually have, if you haven't used it before, a $300 free credit to work on Terra, to play around with it or fun stuff with it. I forgot to show you, but like there's a it usually runs in like cents. So one SciRanger, yeah, so here, if you're able to see it, 40 cents to run one SciRanger count and MK-FASTQ run for like about 5,000 cells. So those $300, if you don't do a lot other things with it, you can do other things with Terra, but if you're just doing SciRanger count and MK-FASTQ, this will actually get you a lot of data. Okay. So let me.
Sorry, Daniel, sorry.
Yeah.
Does it depend on how much data you're uploading to Terra, or regardless of how much data, it's 40 cents?
It definitely depends on the amount of data and specifically how long it runs actually for these workflows. Like if it's running for a day, 2 days, whatever, it will cost more. And the size of data usually will determine how long the alignment and count steps take. So it definitely does vary. You're right. So this is like for a 5,000 cell sample. So you can extrapolate from that as well.
Oh, okay, thanks.
You're welcome. Any other questions? And another thing in terms of prices, you usually, storage is also costly on Google Cloud. So if you don't store your data on GCP, then again, the storage, this $300 will also get you a lot. So you can retrieve your data back to your on-premise once you have processed it, so that you don't have to incur further costs. Thanks for the question. Okay. So I also wanted to show you for these barcode rank plots what a failed run might look like. So the first one that you see here is like a successful run. So you expect to have two cliffs or like knees. So here the first one, and then here the second one, right? So if you don't see something like this, that is alerting you to something going wrong, probably in the experimental workflow, or it could be that you have low quality samples overall. So something like this, where you can see that only 100 barcodes have like this like very small ridge type thing. Same here, only 100 barcodes. And so you really only have 100 cells that are called in this run. So these are examples of compromised runs. Yeah, definitely check the barcode rank plot if you're using 10x. That's automatically created for you, but you can also create that on your own in R. So yeah, good plot to check. Okay, another benefits to using 10x is that it's very straightforward. So like this is our segue to the downstream analysis. So Surat, which is the library, R library that we're going to use, has this read 10x h5 function that will take that filtered or raw h5 file that I showed you in the Google bucket. And so it's very seamless to go from BCL up to the count matrices. You plug it into the cell ranger workflow, get that filtered or raw h5 file, and then read it into Surat, and you're good to go. So that's what it looks like to go from BCL to count matrices. Okay. So the other topic is quality control. So now we have our count matrices, and so we're going to try and do different analysis on it. But before we continue, we want to make sure that our data has only true cells and true cells that are of good quality. So we don't want empty droplets, for instance. So these are droplets that have a unique barcode that are called cells, but actually only contain, you know, ambient RNA that is part of the cell soup and don't actually house intact cells. We also want to remove doublets, which are like multiple cells contained in the same droplet. We want to remove dead or damaged cells, self-explanatory. And then we want to correct for ambient RNA. Some of the floating RNA in the cell soup might end up as part of usually ends up as part of our true cells as well. And so we want to remove that. So all of this is to make sure that our data only contains true cells that are of high quality. So that's our goal going forward. So this is a little challenging specifically because it's hard to identify which cells are poor quality and which are just less complex or small. So like we're going to see different filtering metrics, but then it's hard to know where to set the threshold so that you don't exclude less complex cells as poor quality cells. So we're going to look at some of those, some of the approaches that we're going to take. So the most basic QC that we're going to do, this is almost always a necessity, is we're going to filter cells based on these three QC metrics. So we have number of UMI detected per cell, number of gene detected per cell, and then percent of mitochondrial genes per cell. So
a question just came in, Daniel. Is it necessary to do quality control of raw reads prior to mapping in the upstream analysis?
Yes, it is. What the question is referring to is, so in all of these pre-count matrix processes, there's actually a lot of quality control going on. So there are sequencing errors. This quality value that I showed you in the FASTQs is telling us like how confident are we in these reads. And so we want to exclude reads that are of low confidence and so on. And so there's a lot of things going on behind the scenes that I kind of passed over because it's a high level overview. But the good news is that the tools that we use to convert to FASTQ and then align have built-in QCs within them. I can quickly, I hope you're able to see it here. Yeah, so this metrics summary, so I can, okay, just to, so like things like this, right? Fraction of reads mapped to transcriptome, fraction of reads in cell. So all of these are like quality control things. So I'm on the slides, I'm talking about post these steps, but yeah, so for instance here, you have a lot of detailed quality measures that you can go into in more detail and try to work into your QC filtering. I think like in my own experience, we don't do that as much because again, they are built into the tools. So we kind of default to their default criteria to filter and select only quality reads and so on. You can read more in detail about them, specifically on the cell ranger, so or whatever aligner quantification tool that you use and try to dig deeper. But yeah, that's a very good question. Kind of skipped over it because we don't usually customize those. Whereas this per cell, like post count matrix QC is actually done by us. We have to do it ourselves. There's no black box that's going to take care of it for us. So yeah, very good question. So back to our QC matrix. So we have listed 3 UMIs, genes, and percent mitochondria. I'm going to go back to the count matrix and tell you what each means. So the number of UMI per cell just means we're going to sum up this entire column. So for cell 1, we'll sum up this column and give it a number, 25 plus 1 plus 2 plus 3. And then that's the number of UMIs, total UMIs for this cell. So what's that? That's telling us the number of RNAs that we've captured that purportedly belong to that cell. So we'll do this for each of the cells in our data. And so we'll just sum each column in order to get the total number of UMIs. Number of genes just means the number of unique genes. So for instance, gene M is not detected in cell 2. So gene M is excluded from the number of genes in cell 2. So cell 2, let's say, has 3 genes, whereas cell 1 has 4 genes. So we'll just exclude 0 read genes and then count all the genes. So that's number of genes. Percent mitochondrial genes is very straightforward as well. So we're going to choose genes that come from the mitochondrial RNA, and then compare them, take the percentage as a percentage of the total number of UMIs in that cell. So that's telling us what percentage of the reads come from mitochondrial genes. So what these things are telling us is, so number of UMI and genes detected tell us how many RNA and how many unique genes that we have in a cell. So if those counts are very low, then that kind of indicates to us that that cell is not actually, maybe not actually a cell, or it's damaged and most of the RNA has leaked out, or yeah, something like that. It's just not going to be a useful, so let's say if it has like maybe 100 or so total UMI, it's not going to be informative. It probably comes from a an empty or damaged cell, so we're going to exclude those. Similarly, for mitochondrial gene expression, what that is telling us, so the idea behind filtering based on mitochondrial expression is that when a cell is lysed or damaged, the RNA in the cytoplasm will be lost, and usually the mitochondria will stay intact. And so when you sequence a cell that has been damaged or that has lost most of its RNA, it will have a very high percent of mitochondrial gene expression because those genes which were housed in the mitochondria were preserved. And so that's why we also filter using mitochondrial gene expression. Okay, so it is usually helpful to visualize these QC metrics. So this is like a very fundamental step. We're going to visualize it, try to determine the cutoff that we want to set. There are a lot of recommendations out there, but I would suggest to first look at your data, your own data, and not go with like some default. If your data is telling you that almost all reads are, let's say, less than 400 UMI, then it doesn't make sense to set the cutoff at 400 just because it's part of the Surat tutorial or something like that. So very important to first look at your data, make sure that the cutoff that you choose are reasonable for the data that you have. Another useful thing to visualize is this scatter plot of the different QC matrix. So here we're showing the percentage of mitochondrial genes on the y-axis and number of RNAs. And count RNA is the same as NUMI. This is what is used in Surats. So I wanted to make that familiar to you. So N count RNA is NUMI, and feature RNA is number of genes. So yeah, so we plot these two metrics on a scatter plot, and we can see like some outliers here. And the fact that there are outliers on both ends gives us higher confidence about the need to exclude them. So that's one helpful way to visualize these QCs. It is also often helpful to visualize per group QC matrix. So for instance, if you have reads that are coming from different samples or different sequencing runs or different lanes, whatever technical difference or biological sample difference that you have, it's often useful to visualize these QC features grouped by each, so for each group. So here, for instance, we're visualizing the number of N feature RNA stands for number of genes, and percent empty, percent mitochondria, and we're visualizing it per participant. So this is actually the data that you'll be working with in the lab later. But we can see here that control participant 15 has a slightly, a noticeably higher percent mitochondria and a noticeably lower number of genes total. So that kind of tells us something about first the sample, and then maybe the threshold that we may need to use in order to not introduce biases and so on. So it's always helpful. Also visualize it per cell type, sorry, and that's also helpful. Okay. Another thing to keep in mind when doing this filtering is that the thresholds that you need to set will vary by platform and cell type. So by platform, I mean the sequencing tool that was used. So if it's 10x Chromium or SmartSeq2, that will affect how much, what threshold you should set. So for instance, SmartSeq2 will often yield more genes per cell than 10x. So you shouldn't use the same threshold that you use for 10x as you would for SmartSeq2. So yeah, just be mindful of that. Similarly for cell types, different cell types will have different expected number of UMI per cell. And so you also want to be cognizant of that. For instance, immune cells will have fewer genes per cell than non-immune cells. So here you can see that T cells and B cells have overall lower number of UMI per cell compared to the others. Another important thing is malignant or tumor cells will usually have more genes detected per cell than non-malignant cells. So you can see here that tumor cells often have a very high number of genes detected compared to macrophages, plasma cells, monocytes, and all of that. And so if you're filtering, for instance, trying to filter with a number of genes of, 10,000, and then you'd exclude a lot of tumor cells that are actually cells, but just because they come from a tumor cell, they have a higher number of genes. So yeah, be cognizant of that. Similarly, for percent mitochondrial genes, cardiac cells or like muscular cells usually require a lot more mitochondria because they use a lot of energy. And so they would usually have a higher percentage of mitochondrial RNA. So as you can see here, the cardiomyocytes usually have a higher percent mitochondria compared to other cell types. So Surat, for instance, recommends a 5% cutoff in one of their tutorials. So if you were using that 5% cutoff without actually visualizing the cell type, the per cell type percent mitochondria, then you'd be filtering out all these true myocytes, cardiomyocytes from your analysis. So yeah, just a few things to keep in mind. First, it's usually necessary to revisit QC decisions. So for instance, in order to do this type of analysis, you first need to go through the entire single cell workflow and get your cell types assigned. And then you'd go back and check for the QC distribution per cell type. So you often don't have the cell type when you first start to do QC, you just have like a raw count matrix. So it's like an iterative process. So you start with normally loose QC metrics. So like try to start with as much cells as possible, try to filter out as little as possible, go through the entire workflow, create your cell type annotations, your UMAPs, all of that good stuff, and then go back and visualize your QCs across all these groups just to make sure that the thresholds that you selected make sense. And then you can go increasingly stricter on your QC thresholds and try to see what impact that has on downstream analysis, cell type calling, clustering, and so on. So it's like an iterative process. Start with permissive thresholds and then iterate in order to get better results. Okay. The other side already mentioned make sure to visualize per group QCs. Yeah, so that's the fundamental QCs. So the other aspect of QC is identifying doublets. So doublets, like I mentioned, are two or more cells that are captured together. So in the sequence or in the library preparation and sequencing processes, cells can end up in the same droplet or well, and then they'll be given the same barcode. You have two cells, they're given the same barcode, and in our count matrix, they'll appear as a single cell, but they're actually doublets or triplets or whatever coming from multiple cells. So we want to identify these and filter them out. So that's what we mean by identifying doublets. Different really cool analyses have been done to identify the doublet or multiplet rates in single cell data. This is one of these experiments where they pull together mouse cells and human cells and then do the sequencing, and then we can plot the UMI counts coming from mouse cells against UMI counts coming from human cells. So we can see that some, so these central grayed out cells contain UMIs from both humans and mouse UMIs. And so that's telling us these are actually doublets or multiplets, which contain both human and mouse cell. So there may be like human doublets that are missed from this analysis, or mouse doublets, but it gives us a good sense of like what to expect. So if you have, let's say, 1,000 cells, the multiplet rate is 0.5. But if you have 10,000 cells, multiplet rate is about 5.4%, which is kind of significant. And yeah, so the way there are different approaches to identifying doublets. So we can do, one of the things we can do is look at the total counts, the NUMI that we saw earlier. So genes, cells that have very high number of UMI counts it's an indicator that they might be doublets. So that it's not a very sure thing, like it's not certain, but it's a good indicator that a cell is a doublet if it has like a really extreme amount of UMIs, because it's pulling RNAs from two or more cells. So you can see in this plot that so this experiment was done with knowledge of the true doublets and the true singlets, and here they're plotting the UMI distribution of the singlets and the doublets, and you can clearly see that the doublets have a much higher total UMI count compared to the singlets. And so if we set our threshold, let's say here, then we would be able to filter out a good chunk of the doublets. So that's one approach. Usually, without even going into doublets or singlets, we have this filtering where usually there's like some upper cutoff. So like if the number of RNA count is greater than, let's say, 10,000, we'll just filter out everything. So that's like one of the basic QC steps that also helps us address the issue of doublets. So another approach to identifying doublets is marker gene overlap. So often the cells that are encapsulated together might come from different cell types. So like B cells and T cells are captured together in the same droplet and sequenced together. And if we see that there are markers of both T cell and B cell, then we can group that as a doublet.
So Daniel, you have a question.
Okay.
Is there no danger in ignoring cell intermediates?
I'm not sure which part that came from, but
Maybe
that is.
Zadias, if you're comfortable unmuting yourself, maybe you can help to clarify. Just give him 1 second.
Okay.
Oh,
I can-
yes, Daniel?
Mhm.
We can hear you, yep.
Yes, so there are scenarios, for example, I was talking to this oncologist one day and he was saying sometimes certain medications do not work, mostly because the cells have changed or they've combined two types of cells. So, or they are sort of transitioning from one cell type to the other. And the medications then happens not to work anymore. So in a scenario like that, and then you're looking at the scenario where you were saying you're trying to remove the duplets, the ones that have
Mhm.
more than two cells.
Yep.
Won't we risk a case where we can actually end up throwing away such possible marker cells
Yeah.
like these ones in the cancer system?
Yeah, that's a very good point, Zethias. Thank you so much. Yeah, it's very possible and a very big danger if you're using only marker gene overlap, for instance, to filter out doublets, like Zethias was mentioning. There are some cells that are transitioning between, I don't know if it's possible to transition between T cell and B cell, but there are transitional states generally of that do not actually belong to either predefined cell type. And so if we're just using, for instance, marker gene overlap, then it's a very real possibility that we will filter out these transitional cell types. So, which is why we don't often use like marker gene overlap alone to filter out singlets from doublets. And you can see here, for instance, in this plot, that's what all of these overlaps are. So like we created a marker overlap score, but so these, like the dark red regions are, there's, if we set a threshold here, for instance, all of these are, you know, true singlets that would have been called doublets by marker overlap. So it's not a strict cutoff criteria, and there is a lot of give and take, a lot of pros and cons to each method, but it is an indicator. For instance, if you have two very disparate cell types that you know cannot transition, but you have a cluster that has markers for both cell types. This doesn't often happen. It's not as clean as that, but that is one indication. It's like a heuristic, which means like it's not always accurate, but it gives you an idea when you're doing your analysis. So like you can do like a combination, for instance, if both the total counts is extremely high and the marker genes are coming from two disparate cells, then you can more confidently say that they are doublets.
Daniel, can I just add one thing?
Yep.
Yeah, so that was a great explanation. I'll just add that there's no way to computationally prove something is or is not a doublet. So what Daniel's saying is often we need like biological prior to say how confident we are in the prediction. So the more implausible the pairs of cell types are that are combined, the more we believe the prediction that it's a doublet. So if it's like markers of an epithelial cell and an immune cell in one cell, that seems hard to believe, versus if it's like two different epithelial cell types have markers of both, maybe it's a transitional thing. So there's a biological prior that we often use for guiding, but the only way to prove like something is or is not a doublet, like let's say you find some really weird cluster that has markers of both cell types, is to go back to the original tissue that hasn't been perturbed and do like staining or something for the RNAs or the proteins that seem to be in the same cell, and to actually show in the original tissue that that cell type exists. But yeah, so it's all, so just to keep in mind, this is always kind of a prediction that's guided a lot by biological sort of reasonability.
Thanks, sir. Very good point. Yeah, and as Or was mentioning, it's a very, it's like there's an art to it, kind of like you have to, there's nothing that's going to give you the right answer every time that you run it. So that's a good thing to keep in mind. But we do have tools that are specifically developed to try to give us a better sense of which cells are doublets. Two that I want to highlight are Scrublet and Doublet Finder that you may use in your own analysis. These tools work by simulating doublets, so they'll take singlets from different clusters, try to simulate what a doublet coming from those pairs of clusters might look like, and give a score for each cell by how much it looks like those simulated doublets. So this is the method that is used by Scrublet, I think, and also Doublet Finder, and they'll give you some score of a cell being a doublet. So this is also another method that you might be able to use in order to identify doublets. So it's often a combination of all three approaches to give you a more confident assessment of whether a cell or a cluster is a doublet. Okay, so the other QC that we need to do is detecting empty drops and correcting for ambient RNA. Ambient RNA, I mentioned it before, is basically these. So in the cell solution that we have, there are free-floating RNA molecules from damaged cells, or were just present in the cell solution to begin with, and they will often be encapsulated along with the fully intact cells. And when the cell is lysed and the reads are counted, they will count for that cell's reads. So you might have just these random RNA molecules ending up in your cell's reads. This kind of makes downstream analysis difficult, especially differential expression and marker gene discovery. Clustering is also affected by this because let's say you have a marker gene for monocytes, but it's found in a lot of different cell types just because those genes were part of this ambient RNA. So we want to have tools in order to remove these ambient RNAs from our count matrices. That's where CellBender comes in. It's a really awesome tool that both does empty drop detection and then corrects for ambient RNA. Empty drop detection is, so I showed you the bar rank plots, barcode rank plot in the Cell Ranger from Cell Ranger's output, but it's not the only way to do cell calling. So Cell Ranger has its own method, but we can use different methods. Empty drops is one, CellBender is the other one. I'm not saying one is better than the other, but it's always good to like try different tools, especially if you're seeing that the Cell Ranger cell counts is not in line with the number of cells that you expect. CellBender can be used to call which droplets are cells versus which droplets are not. But more importantly, CellBender specifically does ambient RNA correction. So what it does is it will learn the background noise or ambient RNA. So this region, so this red region of non-cell barcodes, it will learn the distribution of genes in this ambient RNA only barcodes, and then it will subtract those from the actual cells. So the cells that we retain will have the ambient RNA, so these floating RNAs, those counts will be ideally subtracted from our count matrix so that we retain only RNA that came from the intact cells. So this is a demonstration of like the results that they have. So Liz is a very strong marker for CD14 monocytes, just monocytes in general. But if you see this one, this is pre-CellBender and this is B is post-CellBender. So in A, you can see that there's a lot of LYZ gene in like B cells and CD4 T cells, which we don't expect. And it makes like clustering difficult, differential expression difficult, but post cell bender correction, we have this much cleaner looking result. Okay. So the final section is on normalization of gene expression data. Normalization is the process of adjusting raw data to account for unwanted factors. So we want to make sure that, so the raw counts that we get from the cells are not appropriate for comparing with one another. So if I have two cells, so in the figure on your right top, we have two cells that have the same count for each for the genes that are shown, but we can see that cell 1 has more raw reads compared to cell 2, and this might be because we were able to sequence deeper on that cell. It could also be like truly biological difference. For instance, the size may be bigger, and we'll come into the nuances there. But let's say we just sequence cell 1 deeper. That is, we sequenced more molecules in cell 1 compared to cell 2, but the actual number of gene 1 in both cell types were equal. It won't be fair to compare these two gene counts between cell 1 and cell 2. So we want to make sure that the counts that we have are directly comparable. That's what normalization does for us. So often we have two steps in normalization: scaling and transformation. This is like recapping what I mentioned. So if we have so when the sequencing depth increases, the raw expression increases as well. So this is a technical artifact that we don't want to take into account when comparing different cells. So it's just that we sequence deeper. It's not that the number of genes is higher. So we want to correct for sequencing depth, so that in the normalized expression, even though the sequencing depth is higher, than the number of genes that we assign to that cell are the same. Another reason for normalizing is specifically the transformation step will give us a distribution of counts that is more in line with the assumptions of many downstream tools. So usually our DE, differential expression analysis tools, and other downstream analysis tools expect the reads to come from something that looks like a normal distribution. So it's not strictly that, but something approximating a normal distribution. So log transformation, for instance, which is one thing that we do in normalization, allows us to have to go from like a very skewed distribution to something that approximates a normal distribution. This is very idealized and doesn't always happen, but like in an ideal world, that's what we expect. Another reason for normalizing is we often want to compare fold changes instead of so for instance, much easier to say in an example. So cell type A has 1 count for gene 1 and cell type B has 2 counts for gene 1. For gene 2, they have 100 and 200. So if we're trying to compare the differences in raw data, we'll see that the difference is 1 for gene 1, but 100 for gene 2. Even though like in a more intuitive sense, what happens between cell A and cell B is gene 1 doubles and gene 2 doubles as well. So a more intuitive or meaningful comparison between the two cell types is that the number of genes doubles. So in order to make comparisons like that, we we can log to transform our data, which is again one part of the normalization step. This makes our the way we take differences much more intuitive and in line with how we talk about differences in gene expression. Okay. Quickly to go over the actual step of normalization, it's very straightforward. What we do is we first normalize each cell by the total gene expression in that cell. So if we have 500 total UMIs, we'll divide the gene count for each gene by that 500. And then we'll scale it by multiplying by some fixed number. So what we get at the end of this 2 steps is that the gene count that we have is a count per million or per 10,000. So gene 5 in cell 1 had 50 counts per 10,000. And then finally, we log transform the data as discussed in order to get it to a better distribution. We don't need to get into this more deeply, but there are some caveats in how we do normalization. CPM or log CPM that I just described to you has this problem of 0 counts being distorted. So like the difference between 0 and here 1 is they're very close in this raw reads, but in the log 1 plus CPM, it looks as if we have like this very 2 distinct regions. So advanced methods like SC transform might be doing a better job and not have problems like this. So if you want to dig deeper into this, I'd recommend looking into SC transform and other more advanced methods of normalization. I know I went over a little bit, but do we have some time for questions? Happy to take them.
I think we have a few minutes. I'd like to give folks at least 10-minute break between now and the last session of the day. But do we have any questions? Feel free to unmute yourself and ask Daniel directly, or you can add them in the chat. Or if you think of the question later on, you can write it in the Slack channel, and I'm sure that Daniel will be checking there as well.
And Daniel, no need to rush because we can always compress things a little tomorrow with we have a lot of time. I mean, we don't want to compress it too much, but I think it's important that you get through your thing without rushing too.
Okay.
So let's just wait maybe a minute or two for questions to roll in. See if we have any of them. So feel free to ask Daniel questions now or later on the Slack channel. So Peter's asking, are we going to have a practical session?
Yeah, right after this, we're going to go through all the steps that we discussed, starting from count matrices, QC filtering, visualization, and then normalization. So you'll be doing that all on your own. So yeah.
Excellent. Good question, Peter. Any other questions? So I suggest that we take a 10-minute break and that we come back at 3:05 GMT, which is 11:05 Eastern time. Go take a bio break, grab some coffee, and see each other back in this room in 10 minutes. Daniel, thanks so much. We'll see you very shortly for the practical session.
Awesome. Thank you.
Thank you all. Alrighty, everyone. Welcome back from the break. I hope everyone was able to stretch their legs and re-energize themselves for the last part of today. So I think we have most everyone here. Most importantly, do we have Sarah and Daniel? Or sorry, it's Daniela and Daniel. Apologize. Oh, Daniel's just joining us. Let me admit him now. And Daniela, are you here?
I'm here.
Oh, great. Okay, thanks, Daniela. So maybe just give Daniel a second to settle in and then we can begin when you're ready, Daniela and Daniel.
I'm mostly gonna just let Daniel, I'm gonna hand the reins to him for the most part. I'll
Great.
jump in if there's any need, but I know he's got this real under wraps, so.
All right. Daniel, are you ready to begin or do you need a minute or two?
No, I'm good, but we can do breakout rooms, right, Christine?
Absolutely. So you just let me know when
Okay.
you want those breakout rooms to happen and then, or did pre-assign folks to breakout session rooms. So Elliot and I will help direct people into their rooms. So you just let us know when.
Okay. Awesome. Thank
Okay.
you.
Excellent.
Everyone, can you see my screen, the RStudio?
Confirm.
Yeah.
Okay, awesome. So we have I hope everyone was able to sign into their RStudio on the list of files on your bottom right. You can see the HCA COVID-19 QC lab.rmd file. So we're going to be working on that lab in the next 45 minutes or so. I'm going to give you like a high level overview of what we want to do in this lab, and then we're going to go into breakout sessions. There will be one or more organizers in there so that you can ask questions and just work through the script. So it's not, there are instructions detailed in each one in like step-by-step instructions. So you just read them and like execute them. So I'm not going to actually do it live here. You'll just do it in your breakout sessions, okay? And you can ask me questions before we go into the breakout. I'm going to tell you just high-level overview of what's going on in the script. Okay. Thanks, Collins. Okay, so we're going to do, so we'll have a couple sections. We're going to use this nasal swab. It's a COVID-19 data set collected from humans. And we're going to, it's somewhat pre-processed already. So we're going to start with the cell by gene count matrix and a metadata data table. And we're going to create our Seurat object using these two objects. So the first thing that you need to do before you start is this home.dir. You're going to change that to your home directory. So I think all of you would already know that, what your home directory is, but so for me, it is the Chafamo, I guess. And then I'll start executing after this. Okay, so first thing to do. And so we're going to create a Seurat object, and then we're going to do a lot of exploration about what the metadata are, what the counts contain. We're going to have demonstrations of how to get the number of genes, number of cells, how to get counts, all of that good stuff. And then a key part is like at each step, you may just need to execute that section, or you may need to add some code there. So here in this line 96, it says how many cells come from sex equals male samples and how many cells come from sex equals female samples. And it's just a to-do. So you'll find all of the to-dos and you'll add your code to kind of answer that question. So a very similar thing is done above mostly. So you'll just look at how things are done and try to do that yourself. So they should be pretty straightforward. If you have any problems, you'll just ask one of us, okay? And yeah, just we'll generate a lot of different plots and do normalization and finish there, okay? Let me know if you have any questions for me. If not, we'll go into the breakout rooms.
Hey.
Free to ask them at any point. I'm going to just run through it very quickly. So for everyone, you can do just run current chunk through, or like run all chunks below, starting from here on your script, and then just read through the script yourself after this if you're interested. And then yeah, you can get some idea of like the plots that we are able to generate and some of the results that we're able to see, okay? So with that said, so the first thing we do here is load the libraries. Sarah already mentioned these. Surat is the main one. That's the library that we use to analyze our single cell data, store the raw counts, the metadata, the dimensionality reduction, do differential expression, all of that we use Surat. It's one of the alternatives, but for this library, for this lab, we're going to be using Surat. So here in the first step is to read the counts matrix. So here we're using the read RDS function, which just reads in a previously saved R object into our workspace. So Daniela prepared this R object for us previously. It's just the count matrix, which you are seeing here, of genes by cells. So we're just reading that into our workspace. We do the same thing for our metadata. We use the same read RDS object and read it into our workspace. And metadata simply contains additional information about our cells and the samples from which they came. So here you can see the donor ID. So it's telling us this cell came from COVID-19 participant 25. It has the sex, the age, the disease status, and all of that good information about each of our cells is contained in our metadata table. Normally, this was a question that came up in our breakout room. You would not use read RDS, you would use so this read 10x H5 for if you're using the 10x cell ranger output, you could use read 10x H5. You could also use read.csv if you have like a raw a CSV formatted count matrix. So there are different tools depending on the format in which you have your file. So if you have a CSV file containing a table of your count matrix, you do read.csv. But for more custom file formats, there are custom functions like read 10x H5 that can read that data in. So now we'll create our Surat object. So this is the function we use to create the Surat object. We provide it with counts and metadata. Project is just any string that you want. And here we set min cells and min features to 0. By default, create Surat object can do filtering for us. You can see, you can read the detail again by running this help on the create Surat object method. But yeah, so this basically creates the Surat object. This is what we'll be working with from this point onwards. And then, so in order to explore our Surat object, we start by asking how many cells and genes we currently have. Dim, which is just a function to get the dimensions of a table. So any data table that you have, if you do dim, it will tell you the dimensions. So like the number of rows and the number of columns of that data table. It also works on our Seurat object, and we can see that we have 32,000 genes and 6,147 cells. Okay, so once we have our Seurat object, we can get back the counts that we first put in by using this get assay data. Again, I recommend that you look into the help for get assay. Currently, we have it in count slot, and we can visualize the counts that we have. And don't be confused by these dots. They just mean 0 count for that entry. In order to save space, Seurat saves our count matrix in a sparse format, which just means zeros are not actively stored. We just store values that have an entry. Okay. And then very quickly, we can access our metadata from our Seurat object using this @metadata, meta.data syntax. So this will give me the entire metadata for our cells. So in order to get just the column names, I can do call names. Again, it's an R function that gets the column names of a data table. Here we can see what columns that we have. Ncount RNA and nfeature RNA are added by Seurat for us when we created the Seurat object. These are the features that we talked about in the presentation. Ncount RNA is the number of UMIs, nfeature RNA is the number of genes. Okay. We can ask questions like how many cells come from COVID positive samples and how many cells come from COVID negative samples. And we will use this table syntax, which just counts for us the unique values for each, the number of unique values that correspond to each entry. So there are 3,539 COVID negative sample cells and 2608 COVID positive cells. We can do, this was the to do for sex, and we can see the same thing for sex. We can do multiple metadata features cross-tabbed against each other. So there are 1,803 positive COVID negative females and so on. So table is an important function when we want to just do some exploration of our, get some summaries of our data table. Okay, another thing we might want to know is the lowest and highest number of UMIs. Again, we can access our an entire column of our metadata by using this $ symbol. So when I do Seurat.ncount RNA, it's just giving me the number of UMIs for each cell. So it's a column vector, and min is a function, an R native function that just gets the minimum number. So min and max both get us those values. So the lowest is 201, the highest is 4,900. And then again, mean, we can apply any type of function to this ncount RNA vector in order to get some summary results. So mean is just the average. We can do median, mode, and all of that good stuff. Okay. And then we can create a plot of the distribution of this feature. So we're interested in visualizing the number of UMIs and for each cell, and we want to be able to see, so I want to do it without log first. So this was a suggestion by someone from our breakout room. So when you do it without log equals true, so first we're using this VLN plot method from Seurat, which creates a violin plot. The way you interpret this is the red figure is a distribution plot. So the further out, the thicker it is, the larger the number of cells corresponding to that value. So the way I would read this is we have a lot of cells in this 0 to 10,000 end count RNA region and very sparse reads beyond that. And using log equals true just plots the same information on a log axis. So if we go back to the log, and yeah, so this can help us see better the lower ranges of our end count RNA. So now I can be more specific. A majority of our reads have around 3,000 end count RNA, number of EMI, and then a small number less than 300. So we're going to skip these. You can do the same thing with end feature RNA, any type of continuous variable that you have in your metadata. So in order to continue with quality control, we have this line that we execute. So I mentioned that percent end count RNA and end feature RNA were calculated automatically by Surat. Percent empty is not. So we use this percentage feature set in order to calculate the percentage of genes that are coming from mitochondrial genes, the percentage of reads that are coming from mitochondrial genes. So this MT, so mitochondrial genes are always named MT something, MT whatever, C blah, blah, blah. So we use this pattern to identify those mitochondrial genes, and this function will calculate the percentage for us. And again, once this percent.empty is created, so this syntax is just to add it to our metadata. Once it is added to our metadata, we can visualize it just like we did here. So yeah, so here we come to the visualization of all three of the metrics of interest: end count RNA, end feature RNA, and percent mitochondria. So again, we can do this on log scale and just try to better understand where our data lies and what cutoffs might be reasonable. Another question that came up is like, what would be a reasonable cutoff here? Different people would do it differently. There are recommended standards, like, so the low threshold could be like 200 and feature RNA and like 400 end count RNA. But again, that's subjective. It depends from data to data. You want to like exclude outliers as much as possible and also keep as much of the data as possible. Okay, this plot, again, this one is generated using feature scatter, which maps plots two metadata features against one another. So here we're plotting end count RNA and percent mitochondria. So on the x-axis, we have the number of reads in each cell, and on the y-axis, we have the percentage of mitochondrial genes. So again, you can do this with any feature that you want to visualize in the same way. And finally, in terms of plotting, we can again use violin plot function to group our plots by cell type. Here, luckily, we had the cell type in our metadata. We often would first go through the whole analysis, create our cell types, and then come back. This was already done for us. So we have this course cell type annotations, and we can see for each cell type what the QC looks like. And you can see they're very different across different cell types. So yeah, like you can dig deep into each one and see what threshold might apply. You can what biases your thresholds are introducing. So like if we set a threshold at 40,000, then we might lose a lot of ciliated cells and so on. Okay, so finally, to actually do the filtering, we use this subset function. You can again use subset for very different purposes. For here, we're going to filter by end feature RNA, end count RNA, and percent mitochondrial genes. we provide our Seurat object, and under subset, we provide the subsetting criteria. So here, number of genes greater than 200, number of UMI greater than 400, number of genes again less than 6,000, and percent mitochondria less than 40. This is the thresholds that we came to, but again, it's just to demonstrate how you would do the subsetting. Okay. And yeah, finally, normalization. Very straightforward in R to normalize our data. This is the CPM normalization. You can, again, learn more about it in the help section. But what it does is it divides by the total counts, multiplies by the scale factor. Here we're giving it 10,000. People do 1,000,000, 100,000, 10,000, up to you. And then we log normalize. There are different normalization methods, again, that you can read here about each, if you're able to see this, each available normalization method. Log normalize is the most common one. So again, it's very straightforward what is being done, and we can see that as expected, if we exponentiate our log normalized data and then sum all of the columns, we'll get this 10,000 that we, the scale factor that we provide. So our log normalized data will be stored in this at data slots. So from this point on, like, you have a normalized QC filtered data, and then we'll pick up tomorrow on how to do dimensionality reduction, feature selection, and cell type annotation. So that is all for today. If you have any questions, please feel free to ask. Okay, why log2 transformation is important? It is, so first, it transforms the data into something resembling a normal distribution. So if you remember that this plot, it's actually even much more exaggerated than this. There will be a high distribution here and a very big tail. We want to like normalize that into something resembling a normal distribution, not exactly, but something resembling it. So that's one of the reasons we do log normalization. We also want to do fold changes instead of, so going from 1 to 2 and 100 to 200 should reflect a similar type of change in our data. So that's one of the reasons we do log normalization.
Daniel, you have a question from Tina.
Okay.
Tina, I'm happy to read it on your behalf, or if you want to unmute yourself, it's really up to you. The question is, Daniel, can you please go over why log2 transformation is important in quality control?
Yeah, thanks, Christine. Yeah, I was just talking about that.
Oh, okay, just wanted to, glad. Okay.
Any other questions?
Yeah, so I just wanted to add something to the course. So, I mean, we can ask other questions, but then what I also suggest is that if you have any issue or any challenge, first of all, there are lots of materials online. So Google should be your best friend. Try to Google the question, and then probably there are forums that have already discussed this solution. So you can actually go to these forums and pick what they have suggested and apply to your research. So that makes it easier for us if you also want to help. If you have made the attempt to solve it, then we can just add up and then you proceed from there. So always try to make sure you search, because if you are going to learn bioinformatics, single cell in particular, you need to be able to improve upon your information retrieval skills. So that means you should always be reading articles, searching online, and that is what will help you to be expert. We can't make you expert. We can only give you the introduction. So it's up to you to build up from there.
Great. A new question came in. Peter is wondering if these scripts will be shared. I believe the answer is that they will be posted on GitHub.
Yes, exactly. We'll push that to GitHub. It's already there. I'll share the link with you.
Great.
Yeah, and then, probably tomorrow I'll demonstrate how you can also download the files using the RStudio. We can get the files from here as well. So tomorrow, I think I'll do that first thing before we start the exercise.
Excellent. Are there any other questions before we end today's session? Okay, I just want to let everyone know that today's recording from the main room will be posted on the event website in the next 2 to 3 hours. So if you missed a lecture or if you want to rewatch something that one of the lecturers went over today, go back and check out the recording. It is a raw recording, so it's not edited, so I apologize for that. Any other housekeeping or departing words from anyone? Excellent. So just confirming here that we see each other tomorrow at 8 a.m. Eastern time for Sergio and Or's lecture on identification and biological interpretation of cell subsets. So be sure to join us at 8 a.m. Eastern, 12 p.m. GMT for that lecture. And please continue using the Slack channel to communicate and ask questions. Oh, and one more thing before we leave. For the practical that we just did in the breakout sessions, if there are folks who lost internet connection or had to leave throughout the session, is there any way that they can catch up between now and tomorrow?
So the labs are all the RStudio server is still running. So I think the easiest is just to open those up and hit run all chunks. If you have trouble finding where the run all chunks button is, just leave us a message on Slack and we can take a screenshot of how to do that. That's really easy, and just run all that and you'll get all the outputs. Everything should run, and just look at the outputs. And then tomorrow afternoon for all of you, we can answer some more questions that came up. We're happy to, and also post things on Slack. And the lecture notes are also in the GitHub. And Daniel, can you just post the GitHub link in the Slack channel again for people? Thank you. And Dominic has something to add too, I think. Or his hand is raised, but I don't know. There is.
Dominic, you want to unmute yourself? Oh, there you are, my friend.
Yeah, so far so good. Just to add to what some of the instructors have already said, it takes a lot of practice to become a good bioinformatician. So this workshop is a way to get you started for those who are just getting to know R. And most of the comments in there base what each of the codes are doing. So my advice to you is to take your time to understand the codes, and then practice on your own. If you have any challenges, you can contact any of the trainers. And also, as Vincent said, some of these challenges that you'll be having, people have already had it and found a way around it. So you could just Google it or go to GitHub and figure out what people are doing. And then together you can begin to build a good career. Thank you.
Thank you, Dominic.
I posted a YouTube channel that I have for bioinformatics for beginners. So you can check them out. Probably there may be some useful videos for the participants. Yeah.
Excellent. Fantastic. All righty. Well, I think with all of this said, we'll release people for today, and we'll plan to join tomorrow at 12 p.m. GMT. Thank you to
I would like to say,
yes, Collins. Yes.
I'm saying I would like to say that, the login is for RStudio is they can always use it to do it during their free time, and we can provide support through Slack at all times if they have any queries.
Great, thank you. All right, well, we will see you back here tomorrow at noon GMT. Thank you again, everyone.